All right, welcome. Just like that, it's the last week of classes. I can't believe it. I'm sure you're all stressed out. Me too. So I posted, well, I sent out an announcement and I posted a couple of assignments. I did try to keep them nice and small, nice and bite-sized, but also so that we can see some of this material. Now, I decided this would be good enough for practice for the test on Friday, right? And so here, maybe I'll make it a little bit bigger here. And, oh, yeah, they switched the side. Save. I'm gonna, add a page here, put it at the top, because what I want to do today is I posted these notes and I'll reference that. So you can pull those up, or I also posted the Rmd file if you're able to run RStudio on the side, or just sit back and relax. It's whatever you prefer. But I'm going to change the name of this to, what do I usually? I just usually let it name it whatever it says it wants to be. November 30th, 21. I think something like that. And then, so, and I'll crop this up here. Oops. Okay, so for this week, I've kind of taken some liberties. We are talking about logistic regression, but we're just going to focus on the core concepts of logistic regression. So I kind of not talking about all of chapter 4, although we're touching on most of it. Okay, but we've got our test on Friday, which includes logistic regression. So I wanted to get a fair chunk of it out of the way today and then focus, maybe go back and do some more review next day before the test. So my goal is for test 2 to be really easy for you guys. So hopefully that works out. Okay. And it is going to be in the same kind of, hopefully, same kind of format here. It is hidden from students. Dun, dun, dun. Test 2, it'll show up here once it's ready and, or once it's time. So it'll be open on Friday at any time. I think we picked some times like 7 to midnight. It will not be multiple choice, some multiple choice, but same types of questions as the assignments. Okay, and so these assignments use these questions to practice for the test. Okay. So they're not due until, I think I made it, I want to say Monday. Oh man, my calendar is all wrong. So for the assignments, it'll let you check your answers. And I think you get like 10 submissions or something. And if there's something that's not working, then definitely let me know. And I can give you more attempts, but probably if it's not working after 10 attempts, then it's something that we should probably look at. So it should tell you right away if it's right or wrong. You get that very satisfying green check mark telling you what a good job you did. And so that's really nice. You won't have that for the test, obviously, but same types of questions, right? So you can kind of get in the groove. What I decided to do was I also made a bonus lab which is mostly multiple regression. I had 2 multiple regression and 2 logistic regression questions in there, but I decided to cut the last one. So I saw one person had tried it. They're not here, so that might throw them for a loop later when it's been removed. They hadn't put anything in, so I felt okay doing it. But so you can do this bonus lab if maybe you missed a lab at some point and you want to make up for it, and then you can just use this as a bonus lab. So it is applied, and for most of it, you're going to have to just copy and paste the data set into a CSV file. So an Excel file, save as a CSV. If you need help with that, let me know. But otherwise, I think that's the easiest way to bring it into R, and then you'll be able to use it there. Or honestly, you could figure out how to do it in Excel, and doesn't matter to me, but I use R. So you can use those as practice questions. And I mean, if you're happy enough with your grade, then you've managed to do all the assignments as well and get those out of the way. So I wanted to kind of decrease your workload a little bit, but at the same time, really overload you with assignments and stuff. So sorry about that, but here we are. We're going to get through it. Okay, so today I want to talk about, so here, this is what we'll go through today, but here's the RMD file. If you want to follow along so you don't have to type it out, you will have to, I can't remember if I've posted an RMD file before, but if you hit it, it's going to show up like this. So you'd have to copy and paste it into a new markdown document. Okay. I also included it because it shows off some LaTeX that you might want. I don't know, for life, not for assignments or anything, but just in life. It might be nice to have, oh, how did she make that P hat, for example? And it's all in there, right? So you can kind of see the nitty gritty in the background here. Okay. And so here, to open, or to use rather, to use, copy into, or copy all of the text into a new markdown or R markdown document, R markdown file. Okay. So if you want to play along, then it's all there, because what I find is if I'm typing and then you have to type after me, it gets really confusing. For me as a student, I always found that really, really confusing. And I didn't really learn that way. So what I've done is I have included the R code in the PDF, and we're just going to write on the PDF today because most of it is in there. Okay, so anything else that I have managed to forget about? We'll talk more about the final exam, I guess, on Thursday. But basically a mashup of tests 1 and 2. It's going to be a weird situation, but I'm still landing on how I want to go about it. All right. So enough about that. Logistic regression. Okay. So first, I spend the first page just introducing logistic regression. There's a lot more going on, of course, but this is kind of what we need to know. So I want to show you just enough to make you dangerous and then send you out into the world, I guess. No, but as long as we have kind of this stuff on lockdown, then you'll be able to pick up on all the other stuff as you go. So for logistic regression, the key thing about logistic regression is we're trying to predict a categorical outcome, and we're going to focus on binary outcomes. Okay, so 0, 1 situations. So we want to predict a categorical outcome, and you guys have worked in Markdown, so you know that there's no spell check. And honestly, I typed this up earlier today because I thought, oh no, I want to have it summarized somewhere. So I didn't read through it. There's probably typos all over the place. So far, so good, I think. And so a binary outcome is 0, 0, 1 outcome. 1 if it happened, 0 if it didn't. Yeah. And so when we're working with a categorical outcome, usually what we end up saying is we call it a classification method, but really classification is the exact same thing as estimation for a numerical outcome, which is what we did in our linear regression models, is that we're trying to estimate, we're trying to predict a numerical outcome. Now the change is that we're trying to predict a categorical outcome. It gets a little bit confusing because we can have categorical predictors, right? We can have categorical variables of X in our linear model. So our numerical outcome model, right? And we can have numerical predictors in our categorical outcome model. So we're just focusing on the outcome, right? The thing we're trying to predict. In the previous chapter and last week, it was a numerical outcome. Now we're talking about a categorical outcome, okay? And we're going to focus on 0, 1 outcomes. We've seen this before, right? Pretty well every category or any categorical variable can be boiled down into a 0, 1 outcome, right? It happened or it didn't happen. Okay? And so when we're talking about, maybe I'll zoom in here. I didn't adjust the margins or anything. I just kind of went for it. So when we have a binary response, what we're going to see is, well, if we put our, right, if we put our response, binary response on the y-axis, and then we have, let's say, some numerical predictor, X. Okay. What's going to happen is that, okay, if we have a numerical predictor, then we're able to span all these values of X, right? But our response can only be 0 or 1. Okay. So what happens is we end up with dots here and maybe some dots here. Okay. Notice that I bumped the 0 up a little bit because otherwise it gets too crowded on the x-axis. Of course, the x-axis is at y = 0, but just to visualize it, I bumped it down a little bit. Okay, so now we have this type of scenario, right? For these values of X, I get a 0 response. And then at some point for these values of X, these larger values of X, it looks like I'm getting a 1 response. There is probably likely going to be a little bit of overlap here, but overall we want to know, okay, if I have some outcome for X, right? So if I have some value for X, what's my most likely response going to be, 0 or 1? Right? And so that's the model that we're trying to build. So what happens is, well, in theory, we could fit a linear model through here. The problem is that that doesn't do a good job at all at predicting any of these outcomes, right? It does a great job at this little area here and at this little area here, but beyond that, it doesn't do a good job at all, right? So here, this area becomes a problem. Okay, maybe I shouldn't overlap the text. There. So these parts of the line become a problem. And even here, this doesn't do a good job of predicting. So these parts of the lines, so extending past 0 and 1 to negative infinity and positive infinity, are not doing anything for us. They can't happen because our options are only 0 and 1. And even in here, it's doing a poor job predicting the response. Oops. Okay. Now, I'm going to try to spend as little time as I can. I did sort of develop it here, kind of the reasoning behind doing it. But what we're going to do is we're going to try to fit a model that is restricted between 0 and 1, because we know that we can only have 0 and 1s. Now, so what we want to do is we want to feed it some value of x and then get a value between 0 and 1 inclusive. That should remind us of a probability. A probability is a value between 0 and 1, and it's restricted between 0 and 1 inclusive. Okay. So here, when the response variable is binary, all the data will be shown in rows at 0 or 1 in a scatter plot, right? So just like we saw here. And fitting a linear model can be done, right? It can be, but it's not appropriate because it will not describe the relationship well. Okay, so here's kind of the development, and you can kind of tune this out if you want to, but here's the reason why. Couldn't get away from that theory, right? So we know that the linear model, it extends from negative infinity to positive infinity. And we want to change that so it's restricted between 0 and 1. Okay, so what we do is we model the estimated probability, which we call p hat, which is going to result in an S-shaped model restricted between 0 and 1. So what we're going to get is we're going to see kind of something like this. Okay. And maybe here, there. So, but to get there is a little bit tricky. We can't just find the probabilities and then be done with it and then map those out. We need to kind of manipulate what we have. So what we do is we take those probabilities, right? And so here, the probabilities that we're going to find are going to follow this kind of S-shaped curve. So it becomes this S-shaped model. Just like before, it's only really possible to see the relationship if you have one predictor. As soon as you extend it to 2 predictors or 3, anything more than 2, we can't map it out anymore. So I'm going to focus on just one predictor here to start. And then the same idea applies, but we can't really put our finger on it and visualize it anymore. Okay, so what we have is, okay, so the model that we want is restricted between 0 and 1, which sounds like a probability, right? And it is, it's going to be a probability. Now, what we want to do is basically, and I'm imagining I'm grabbing those ends of the green line and I'm just kind of straightening it out. So how can I, because if I can do that, then I can apply a linear model, right? So if I can manipulate my responses or my outcome for my model to be linear, then I'm off to the races. Okay, so how we do that, and this is established, so you don't have to develop this, but what we do is we consider the odds ratio. We later take the log of it, but first we consider the odds ratio. And here, I want to highlight that the odds are often incorrectly used. So I see this a lot. People will use the term odds to replace probability, but that's not true, because the odds, or the odds ratio, OR, you'll see in the assignment, they say OR, calculate the OR. And so that's what they mean. The odds ratio is P hat. Now that's a probability divided by 1 minus P hat. So the probability of an event happening divided by the probability of an event not happening. Okay, so the odds ratio, if the probability is I don't know, 2 over 3, right? 2 and 3. Then the probability of it not happening is 1 in 3, right? If the probability of it happening is 2 and 3, then 1 in 3 is the probability of it not happening. So then if I take 2 and 3 over 1 and 3, fraction over fraction, I flip and multiply, then I get 2 over 1. So the odds ratio, or the odds, would be 2 to 1. Okay, so that's really important, just to kind of have that stopper in your mind saying, okay, if I want to say odds, I remember it's not the probability. You don't have to remember exactly what it is, but you have to remember it's not the same as the probability. So the odds are actually the probability of an event occurring divided by the probability the event doesn't occur. Okay. So we remember that probabilities range between 0 and 1. So the odds ratio, right, if P hat can be between 0 and 1, and then if I divide by 1 minus that, then the odds ratio are going to range between 0 and infinity. Okay. If we take the natural log of that, right, the natural log of something ranging between 0 and infinity, then what I get is I get a result that's going to range from negative infinity to infinity, which is a linear model. Okay. So the natural log, the natural log of the odds ratio is called the log odds, or the logit of an event. I'm going to use those interchangeably, mostly to get you used to it, but also because I flip-flop. It depends on, what sounds better when I'm saying it is probably what it comes down to, right? But we need to be flexible, and so the log odds or the logit, those we use interchangeably. And so what's really cool, I think, is that, okay, once we have taken the natural log here, then we can apply a linear model. Okay, so here we've got the logit, log odds, or the logit. But this is just a linear model with Q predictors. So that's really nice, right? Because we know how to fit a linear model like this one, right? And so let's see here. Can't remember if I talked about the natural log. I'm trying to think when in my other class I talked about the natural log. Might have been in data science. Anyways, for our purposes, we always use the natural log in statistics. So unless you're in physics, then hey, that's ringing a bell. Anyways, so unless you're in physics, then we're going to be working in log base E, which is the natural log. And so sometimes you'll even see just log here, but what they actually mean is the natural log. So here I've specified, but it will always be the natural log. Okay. Confusing, but once you get the hang of it, it's okay. Okay, so one thing is that instead of having a nice tidy y hat here, right, what we're actually predicting is the logit, right? So we're no longer predicting a y value explicitly, we're predicting the log odds, right? And so the natural log of p hat over 1 minus p hat. But what we actually want is we want to shake out the p hat, right? We want to get an estimate for p hat here. So what we can do is we can build our model with the log odds as our response, and then we can find these coefficients, and then we can plug in values of x that we want, and then we can use that to solve for our p hat, right? So the difference between a linear model and a logistic model is that our interpretation of the coefficients, and maybe I should specify that here, interpretation of the coefficients will need to be in terms of the logit. Now that's difficult, right? We're not going to have to do that, because what we're going to do is we're going to unravel these estimates into p hats, okay? Now, the reason that we are trying to solve for our p hat here is because that's what we were trying to find, because we want to find the probability of being in class 1 versus the probability of being in class 0. Now, the p hat is going to be the probability, p hat is the probability of being in class 1. Now, class 1, I'm using in a general sense of whatever the one outcome is in a binary situation, right? So class 1 is just generic for a one outcome, right? And the one outcome, you can change it. So usually it's going to be whatever you're interested in. Okay. And so what we can do is we can rearrange the model, and we can solve for p hat. Now, what I want to do is I want to show, and I want to work through together how we kind of unravel this to solve for p hat. Now, if I just ask you to do it, I hope that that's pretty obvious, but I do want to do it step by step together, just so we've seen it. Okay. So here, so if we have the log odds, p hat 1 minus p hat is b0 plus b1 x1 plus all the way up to some bq xq. Okay. Using q for the number of predictors. Sometimes we'll use p, it really doesn't matter. Okay. Now, what I'm going to do, because I don't want to write this all out every time, I'm going to cheat a little bit and just copy it. Hopefully it works out. And let me add a page here. Okay. Maybe what I'll do, oh, I wonder if it deleted what I had saved. Anyways, so if I want to solve for p hat, here, then what I can do is I can say, okay, well, e to the logit, the log odds, the natural log of p hat over 1 minus p hat is e to the power of what I had pasted there, or copied rather. Okay, so it's e, so you raise the whole model to the e to the power of that. Okay, now this is gonna we raise it to the e because that's how we cancel the log. So now what we have is p hat over 1 minus p hat is, and I'm going to copy e to the power of all this now. Copy. There. Okay. If I'm trying to solve for p hat, how am I going to do that? Well, I'm going to multiply both sides by 1 minus p hat. That's the easiest thing to do. You could get weird with it, but why? P hat is 1 minus p hat times that e to the power of whatever. Okay. The model, the linear model. So if I expand this out, then I get p hat is e to the linear model minus p hat times e to the linear model. I'm going to need to shrink it up to fit it on the page. So then I can subtract, or I can add, sorry, p hat times e to the linear model to the other side. So then I get p hat plus p hat times that linear model. Make it a little bit smaller, is equal to that linear model. Yeah. If I factor out a p hat, I get p hat times 1 plus that linear model, or e to the linear model, I should say. I keep skipping that, but I shouldn't. These little dots got lost. Is that. Okay. Finally, I can solve for p hat. P hat is that e to the linear model divided by 1 plus e to that linear model. Okay. Now, what you'll notice is that, so sometimes, and I saw on the assignment, sometimes we can just use this for our p hat. Okay, so we can use this, we can, or we could stop here and use this equation to solve for p hat given a linear model, Or what we could do is, if we don't want to plug in the model twice, what we could do is factor out an e to the linear model from both 1 and e to the linear model. So I just want to show that, right? So then optional, we factor out e to the b0 plus b1 x1 plus bq xq from the denominator. By rewriting, maybe I won't show it, by rewriting 1 as e to the b0 plus b1 x1 plus bq xq minus, as long as I have e to the 0, e to the 0 is 1, right? So I can replace 1 with this mess. Okay. But then by exponent laws, I have e to the b0 plus b1 x1 plus bq xq. That's the one I'm going to want to cancel with the numerator, right? That's my common factor that I'm trying to pull out. Okay. But then my exponent laws say that I still have e to the negative b naught plus b1 x1 plus bq xq. Okay. So once we do that, we're going to end up with this logistic function. After we do that, we end up with the logistic function. Both of them work, okay? But just wanted to show you where things came from because, oh, wow. Because I didn't want you to be confused when you saw it on the assignment. Okay. So here, this is the one that we're going to be using. P hat is 1 because I factor out that e to the linear model. And so then I'm left with 1 over 1 plus, because I do a little switcheroo here, e to the negative. Now that's really important here, is that that's negative in front of that linear model. Once we've done that, then what we can do is we can predict values using the linear model, and then I can plug that in and take e to the negative of that plus 1, and then divide 1 divided by that. Okay, and so given output for a linear model as well as the values for all predictors, we can calculate the predicted probability using the logistic function. Now, if we have a probability of being in class 1, so if we just kind of took a step back and I told you that the probability that this observation is in class 1 is 0.35, what would you classify it as? Just kind of gut feeling, class 0 or class 1? Probably class 0. Why? Because it's less than 0.5, right? And so we use that same cutoff value as we kind of would intuitively, right? Because if it's less than 0.5, then we say, okay, well, that's not likely. Then it's more likely that it's in class 0, right? Whereas if it's more than 0.5, then we say, okay, sure, I'll classify it as class 1. Okay, and so an outcome is classified as class 1 if the probability is greater than or equal to 0.5, in case there's ever an exact value of 0.5. Can happen, but it's pretty rare, and classified as class 0 otherwise. So you can use other cutoffs, but 0.5 is of course standard. Okay, so what do we do when you live in a shoe? Let's see here. How do we actually do it? What can we do here? Okay, so what I want to do is I want to use this example, and I've pretty well outlined the core scenarios that you'll need to be able to deal with on the assignment, and then should be pretty good. So I stole the data and the description from Open Intro because it's really a cool example, or cute at least. Oh, well, not exactly important, but where is that little possum? They have, oh, here. Oh. I guess I should keep the photo credit. I am shamelessly stealing it though, so whatever. So here's this cutie little possum that we're talking about. Maybe he's not that cute, but he's cuter than an American possum, that's for sure. So anyways, this is the animal that we're talking about. Doesn't matter, we can talk about anything. But so this is the one that I stole from Open Intro. And I think you guys used Open Intro for Stat 230, so pretty typical. So the common brush-tailed possum of the Australia region is a bit cuter than its distant cousin, the American possum, opossum, although I think we can say possum, jury's out. We consider 104 brush-tailed possums from 2 regions in Australia, where the possums may be considered a random sample from the population. Great. The first region is Victoria, which is in the eastern half of Australia and traverses the southern coast. So we start here in the, east, and then we work our way through the southern coast. I'm not too familiar with Australia yet. I don't know. I just want to be. And then the second region is New South Wales and Queensland, which make up the eastern and northeastern Australia. So we're going to use logistic regression to differentiate between possums in these 2 regions. Okay, and so the idea here is you have collected some possum and you have information that you can measure, like you have the head length, you have the skull width, you've got the total length, you've got the tail length, you can find the sex or the gender, right? And so using this information, are we able to classify this possum as coming from region 1 or region 0? So coming from the Victoria region or the New South Wales and Queensland region. We're going to focus on just 2 regions because otherwise we don't have a binary outcome, right? And so what we have, some outcome variable, we're going to call it population, or it's called population. I think it's actually called pop, which we'll see here. But it's going to be a value of 1 when a possum is from Victoria and 0 when it's from New South Wales or Queensland. So we've got these predictors. So if we open, and just as a side note here, if you haven't installed the Open Intro package ever, first run install.packages Open Intro in quotes, but you only need to run it once. Okay? But only do this once. Okay, so you only need to install a package one time, and then it'll just be there and you have to call the library so that it knows, oh, hey, use these tools. And same thing with the knitter package. If you haven't installed it, you'd have to install .packages in quotes knitter exactly as it's called here. If you have trouble with that, then let me know and I'll help you out. But for now, let's just assume that it's all up and running. So the possum data set is stored in the Open Intro library. If you want to see it, you could save it as possum or something else, and then you can access it that way, which might be nice, but you don't have to. Okay, so I pulled up the head of the data set, which just pulls up the first, I guess, 1, 2, 3, 4, 5, 6 observations. You can adjust how many you want to see, but this is just to give us an idea of the data set. So we've got this site variable, we've got a pop variable. Notice that it says Vic, 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 and then it'll say other, other, other. We'll look at that. We've got the sex stored as male, female, which maybe we'll want to change, but I'm going to leave it as it is. We've got the age in years, and then the head length, the skull width, the total length, and the tail length. And I just assume it's measured in inches. They actually never mentioned the units, so I'm going to assume it's in inches because they are American. So, and they hate centimeters. Although looking at this little guy, maybe it is in centimeters. How long do you think that tail is? Now, I'm the opposite end. I refuse to use inches, so I actually have no clue. Well, I have some clue. Maybe it's in centimeters. He doesn't look that big. 32 inches. 32. Yeah, it looks like centimeters. This thing's huge. Let's see here. 32 divided by 12. Well, 2.5 feet for a tail. Yeah. Nope. Okay, so let's say in centimeters. Yeah, it's like a wildcat. Although, yeah, confession time. Tiger King makes you wonder, right? So anyways, probably centimeters. I don't know. I just went for inches because I know that the authors are Americans. So, but here they are, throwing me for a loop. Anyways, let's see here. Okay, so we've got this information, and I was poking around. I looked at a couple of things, but some of the things that I thought were useful was to look at the names. Now, notice that I'm wrapping everything up in cable when I can. And cable is what generates this nicer looking table. So it's a knitter table, cable. So if you haven't used cable before, it takes a table and it turns it from kind of nasty looking R code into nice-ish looking markdown. So when I run the names of the possum, but of course it requires the knitter package. Okay. So when I run the names of the possum, then I have these names, and these are the variable names that my data set will understand, or that R will understand, right? So even though it said head length in the description, it looks like they changed it to head underscore L, but I mean, we understand what that means. So what I wanted to do was I wanted to look at possum, so a table, so a summary of the pop variable. Oh, nice. Hey, you guys went deeper than I did, in centimeters. Nice. Then I think it's safe to assume that it's all in centimeters. Great. All right. Then I think there's another typo where I say inches later, but we'll know. Okay, so what I saw was that in Victoria, there were 46 possums from Victoria, and 58 of these 104 were from the other regions. Now, even with just this information, we can do, calculations and whatever, but that's not what we're here for. I just wanted to get an idea of what the different outcomes were and make sure that it's binary. If these variables were not binary, with two outcomes, it is binary, but if it wasn't, we would need to force it. Okay. So here it looks like they've got an other category. We would do something similar, right? We would pick a category that we are most interested in predicting, and then throw all the other categories into an other category or some lumped category. Okay. And so these are, oh, that's not a curly bracket. These are the variable names we can use. Okay. In our code. Okay. So there are lots of fancy ways that you can do this, but my main concern was just assigning, instead of having it stored as Vic and other, which R recognizes as text, because then what it does is it says, it adjusts the plot and says, well, you can't really plot a categorical variable against the on the y-axis, so here's a nice stacked bar chart instead, which is not what I wanted. And so to get away from that and to be able to plot it the way I wanted to, I'm going to change the Vic, all the possums that have a code of Vic, I'm going to change them to 1. Now, instead of writing over the population column, what I'm going to do is I'm going to add another column. Okay, so that's probably the safest way to do it. Don't overwrite anything unless you're feeling confident, then you can overwrite it. But what I'm doing here is I'm going to create a new column on possum called pop dummy. So a dummy variable, right, is a 0, 1 variable, or I guess in machine learning, they call it a 1 hot, which I think is really funny. And that's exactly what it is. It's just an on-off switch. And so if it's a 1, it's in Victoria. And if it's off, then it's not in Victoria. So what I'm going to do is I'm going to use an if-else statement. There are tons of ways you can do this, but I've decided to use an if-else statement because I find that it's the easiest. So if the possum $pop variable is equal to, notice the double equal sign here, because it has to be a logical statement, is equal to Vic, and you have to spell it out exactly as it's written, right? So I made sure that I copied the Vic, then give me a 1. If it's not that, so if that's false, then put a 0. Right? And what that's going to do is it's going to run through the whole data set, and it's going to produce a 1 or a 0 depending on if there's a Vic in the pop or no Vic, which would be other. Right? So this would even work even if there were more categories here. So that's really nice, right? Because all you're saying is you've picked the one that you want to code as a 1. Well, I'm glad to hear it. So even if you code it as so as long as you pick the one that you're going to code as a 1, then all the other ones can be 0s. Okay. So if we plot, so now I'm able to plot this pop dummy, because then it just sees 0s and 1s and says, oh, that's numerical, so I'll put that on the y-axis. And I decided to focus on, I picked tail length somewhat arbitrarily. I went through and I played with a few of them, and I wanted one that had some sort of shift. A lot of them were showing like this. So I wanted one that had some sort of shift. That doesn't matter. I just wanted it to show some sort of S-curve. Otherwise, it can be kind of defeating. And then I tell it that the data I'm using is the possum data. Okay. So when I look at this, and maybe I'll make a note here that picked arbitrarily if I can spell arbitrarily, arbitrarily. Okay, sort of. So when I look at this graph, and I didn't clean it up or anything, I just wanted to get the plot out there. So what I'm seeing is, okay, so here's my other category. And here are my Vic possums. Okay. So what we're seeing here is we have all these ones. Okay, so all of these tail lengths are ones. And then all of these tail lengths are zeros. So we're going to use this data to be able to predict the probability of being either in the 0 category or in the 1 category. Now we can see that, okay, there's going to be some difficulty here. Let's say if the tail length is 37, hey, why is it doing that? Well, looks pretty reasonable to be in either one, right? So how are we going to decide? Well, we're going to let the probability decide for us. If the probability is less than 0.5, then we're going to classify it as a class 0. And if the probability of being in group 1 is more than 0.5, then we group it as group 1. Okay. So just like before, I'm going to focus on one predictor because that's the only one that we'll be able to see and plot and look at, right? Kind of get a handle on. And then we'll extend it to multiple predictors, right? But the idea and the process stays the same. Okay. So what I've decided, just to show you one example, right? We're first going to consider the relationship between the regions and the tail length of the possum. So just focusing on one predictor. Specifically, let's say we want to predict the probability of being in class 1 if the tail length is 36 inches. The reason I picked 36 inches is because it's the first observation in the possum data. So we'll be able to check it and confirm it very easily. Okay, and maybe what I should do is I shouldn't have the 37. Maybe let's reference the actual one that we are using. Okay. Just as hard, right, to figure out which class it would be in. Okay, it happens in both, right? But which one is more likely? Okay. So what we do is we're going to use the GLM command. So you've used the LM command to build linear models, and now we use the GLM, which is a generalized linear model function where we can specify that we're building a logistic model. And we do that by saying family equals binomial. So I'm going to name this log mod because I want to have different names for my models because I'm going to be building a couple of different models. So you want to have something descriptive, and I choose log mod. Log mod is going to be a GLM, so a generalized linear model that models, and just in case it's unclear, this is a tilde here, it models the pop dummy as the response against the tail length. Okay, so here, this is our X tilde, oh my gosh, it's not our X, Y tilde X. I don't know why I screwed that up. Anyways, you could say possum $ pop dummy tilde possum $ tail length. That's often what I do if I don't think I'll have to change the data set anytime soon. Then sometimes I'll hard code it because it makes it easier to see. But in this case, I just wanted to say, okay, the data is the possum and the family that I'm using for my GLM is the binomial. Okay. And that's what tells it, okay, what you're actually going to be doing is you're going to be using the log odds or the logit as your response. Okay, so it does everything in the background. if you run the summary of the log mod, and I tried to cable this, but it doesn't like it because it's not a table, it's multiple tables. But I'm sure there's a nice way of printing it, but I just couldn't. I didn't research it. I didn't find it, I gave up. So the summary of the log mod, and maybe it's nice to see it like this, kind of nasty. So the summary of the log mod is going to look like this. First, it has all the information that we put into our model, just as a reminder that this is the model we're talking about. It looks at the residuals, and we're going to ignore that. That's bad, but we would analyze the residuals as part of our goodness of fit testing, right? Does this model apply? Is this a good model? We can look at the residuals for that. But the meat and potatoes are here in the coefficients. Okay. So the rest of this stuff you can, I don't want to say ignore, but you can parking lot it forever, or, you know, until this comes up again. But for us, we're just going to parking lot it. There's the AIC, which we could use. That's basically the R squared equivalent, because we won't have an R squared. We're going to have, because we have a categorical response. So kind of, but we'll leave that. Okay. So here now we have an intercept and we have some slope coefficient, right? And so we still have the probability, the p-values for each of these, which is great. So it looks like both of them are contributing to the model. And so that part we look at the exact same way that we did before. And so these are both helpful in predicting which, or the tail length is looking to be helpful in predicting the class. Now, it will be because it's the only thing we're giving it. If we added more variables, then maybe it won't be as significant anymore. So we'll look at that. Okay, so I want to add a page here. Okay, so from, oops, come on. Hey. From here, I want to focus on this. Okay, so what this is saying is that it's saying that the natural log of p hat over 1 minus p hat, oops. You mess up those brackets when you're typing, not usually when you're writing, but I managed, is going to be some b naught plus b1 x. In this case, we only have one x, so that's fine. So in this case, it's going to be 25. Hey, it's not printing properly. I read that sometimes I guess the pen will act like that if the screen is dirty, but I keep cleaning it and it's not, I don't know, it's not helping. 25.5662 plus negative 0.6996 times the tail length. Okay. So what we're going to do is we're going to use this because our goal was to predict the class or the probability of being in class 1 if the tail length is 36 centimeters. Doesn't matter. If it's 36 units withheld. Okay, so how can we do that? We have a tail length of 36. Okay, so using tail length equal to 36, we find that this is equal to 25.5662 minus 0.6996 times 36. Okay. So let's see here. 25.5662 minus 0.6996 times 36. Make sure you use brackets. And I said that, but I didn't actually do it. Hopefully my calculator's clever enough. I'll check it. 0.3806 is what I get. Let me just check. 0.6996 times 36, negative of that, plus 25.5662. Okay. But remember that this is actually the log odds but we want to solve for p hat. Okay, you can do that. Awesome. Thank you for confirming because I missed it though. So we want to solve for p hat. So you can do that. You can unravel it. Or we can just use the formula that we looked at before. So you can derive it or use the logistic function, which we ended up at p hat is 1 divided by 1 plus e to the negative b naught plus b1 x in this case, right? Notice that it's negative, and also, oh, keeps doing that. This is 0.3806 from above, right? So we already found that. So this becomes, so p hat becomes 1 over 1 plus e to the negative 0.3806. So carefully doing this, making sure you remember the negative here. So I'm going to make it negative. I have it on my screen here, and then I'm going to take e to the power of that value if I don't mess it up. Okay. Then plus 1, and then 1 over that. And I get p hat is 0.5940178075. Okay, nice. Would I classify this as a class 0 or class 1? Well, it's borderline, right? But I would put it in class 1. That's my best guess. I understand that it might, it can go either way, but that's the truth for any of these classifications, right? I could be wrong. And that's a whole other area that we could talk about is how do we classify, or how do we talk about our errors in our classifications? We're going to ignore that aspect. But of course, there's a chance that I'm wrong. And how many did I get wrong if I compare it to if it's actually in class 1 or not? So here, we would classify as group 1, right? Because it's higher than 0.5. So what we can do is we can use the predict function, which we're going to apply it to all of our observations in our data. And then we're going to get a predicted value or a predicted probability for each of the possums. Okay. So the predict function will do this calculation. Oops. For each observation in the data. Okay. So I'm creating a new column called p hat, okay? And I'm attaching it to possum. And what it's going to do is I'm going to predict, and it needs the model that it's going to use to predict. It needs the log mod and apply it to the possum, and it knows that the X variable is the tail length, right? So just go into possum and find the tail length, and then the type is the response, which because we're trying to predict the response. And then if I look at the possum data now, I have the original data. I've also got the pop dummy, which makes sense that it's all ones because all of these are in Victoria. The first 6 are all in Victoria. And then we've got the p hats for all of these. Now notice we're slightly off, but that's because we were probably given rounded values in our coefficients, right? So R doesn't need to round any values. It can only show you so many values, right? And so that's what we have to work with. But then it's able to use non-rounded values, right? And so here versus, what did we find? 0.594. Copy. Oh. Oh, don't need that anymore. We were given, or we were using, I should say, because we were given, but we were using rounded values for the coefficients. So that's why it's so important that you don't go ahead and do any rounding. It's already giving you rounded values. So you want to use all those decimal places that you're given so you don't lose anything. So we were given rounded values for the coefficient. Okay, so the one that I'm looking at here is, this is how I chose the 36, right? And so now I have this prediction that I can compare it against, and it is in class 1, and I'm classifying it as class 1. Now, notice in the third observation here, the predicted probability of being in class 1 is 0.15. So you would classify it as a class 0 when it's actually in class 1, right? But so here, using this model, these two observations would be misclassified. Okay. That's okay. We're okay with, we're predicting, so we're just doing our best here, right? And so we can build a different model and see if we're able to reduce the number of misclassifications, right? And so sometimes it's worse to misclassify as a class 1 versus a class 0. So you might want to, you would have to make adjustments that way. But like I said, we're going to table that discussion, and just be aware that, of course, we would be misclassifying at some rate, right? And how do we know that? Well, because we can check, right? We can check what class they're actually in. So we can now plot the predicted probabilities. So what we do is, I've got this plot, and it's the plot that we started out with, right? And then I'm going to add the lines of the p hat, okay, against the tail length. So now I'm going to plot the tail length or the p hat against the tail length, and the possum data is what I'm using, and the line type. LWD is the line type, I think, and it's going to attach it with a line. What I was hoping for was a nice S curve, and I guess I could maybe squint and see kind of an S curve here, right? But I was expecting an S curve. Okay. That's okay. We can do that, okay? But what we'd have to do, and I know you've seen this before, is we generate, instead of just having these values of X that we have in our data, these 104 values of X, I even said, this doesn't look very nice. We can smooth it out by creating fake X values. Okay, and so what we're going to do is we're going to run these fake X values from the minimum in our data set, which I think is 32, to our maximum, which is 43, I guess. We don't hard code that. What I want to do is I'm going to create something called new data, a new data set. Okay, it's going to be a data frame because I'm going to add more columns to it. But then the tail length of this data frame, so I'm naming a new column tail length, and it's going to be a sequence from the minimum from the possum of the tail, possum tail length up to the maximum, and I want the length to be 500. So I'm specifying a list of 500 values between 32 and 43. Okay. So here, I want a list of 500 values, or maybe I should say a sequence, just to match the sequence of 500 values between 32 and 43. Okay. So now, if you're running this in your R, I think not randomly, I think it just generates it. So it takes the distance 32 and 43, and it divides it into 500 equal intervals, and then just produces a point at those values. So we force it to be 500 points. And you can imagine if you force 500 points in between here, then you're going to be able to smooth this curve out. Okay. And so the new data generates 500 values or 500 points in this stretch. Okay. Good. So when we want to smooth out graphs like this is the trick that we use. We say, okay, well, how about I pretend to have a huge number of observations in this stretch, and then if I connect them and I use little dots and I connect them, then I'll be able to get a smooth line. So then what I want to do is into our new data, I want to add the pop values, but I want to predict the probability for each of these new X values that I've generated. So here, right, so here, generates 500 predicted probabilities. So we use that same predict function. We're using the log mod, and we're applying it to our new data now because I have a tail underscore length or tail underscore L in my new data because I forced it to have it, and then I can predict the response. So now how these plots work is we have to have the bare plot. So the bare bones plot, that's the same one that we've been looking at all along. Okay. And then what I'm going to do is I'm going to add lines. Now, ours is kind of weird this way. And especially if you've worked with ggplot, then you know it's just a layering. Okay. And so what we can do is we can say, okay, now add lines. So use the lines command and add lines that connect the predicted probability against the tail of the new data. So this is plotting the 500 data points in your new data. Plot the 500 data points. And then I've added an AB line or an AB line, which is horizontal at 0.5. I added this as the cutoff. Added this to show the cutoff. Okay. Oh my gosh, I'm all out of time, but I just want you to see the fruits of our labor. And I forgot. So sorry, guys. Anyways, so here now we've got this beautiful line, which is actually 500 points connected by a line. Beautiful. So here, this is actually 500 points connected by a line. All right, just so it's not, so you don't think that there is a secret line. No, whenever we draw a line, we're just drawing points and connecting lines or connecting them with lines. And then here is our cutoff. Okay, so we'll pick up there because I've got a couple of more things I want to show you, but we'll pick up there on Thursday. Nice. So nice, right? But I'm all out of time and I apologize, but pretty fun stuff. All right. So if you have any questions, let me know. Otherwise, I'll see you on Thursday.